participant for being here. So today we'll talk about part of my PhD thesis. I think that this long title contains mostly all the keywords that we will see together for today. So this is the plan of the talk. I will start by stating general questions, and then I will spend a few times to talk about earthquakes and infinitesimal earthquakes. And then I will explain to you the mass proof of Thurston earthquake theorem by introducing the anti-de Sitter geometry. So this, I think, will be the first part. And then in the second part, we will see this exotic geometry, which is called half-pipe geometry, and its relation with vector fields on the hyperbolic plane. And then if I have time, I will talk about work in progress. Okay, so let's state a general question. I think that everyone can understand these two questions. So you take D2, the disk, and S1, the unit circle, the boundary of the disk. And then you state the following question. For a given homeomorphism F, sometimes you need more regularity, but not too much. I mean, we need maybe sometimes quasi-symmetric map. Then the question or the goal is to find a good extension of this map F to the unit disk. Namely, we want to find a map from the disk to the disk which extends this map F. After that, I will explain what do I mean by good, but typical class of maps that we want. For example, if you start from a rotation of S1, then the extension will be the rotation itself, okay? Or more generally, if you take isometry of hyperbolic plane, the extension will be the isometry itself. Okay, so there are a lot of such extensions. So these are example. There's, for example, the dual D-Earl extension, which are a particular class of quasi-conformal map. There is earthquake map, which was introduced by Thurston and then studied by other people like Mess. There is also a minimal Lagrangian diffeomorphism, which was introduced by Laborie and then extended by Bonsanti and Schlenker. And there is also a harmonic map. So this question, I don't think that it is very strange, even for PDE people. This is known as Dirichlet problem, for example. You have some boundary condition and you want to find harmonic extension inside the disk. So for today, we'll not talk about analysis because I will focus on these two class of maps, which are in blue, because their proof, let's say, comes from the study of a particular geometry, which is the anti-de Sitter geometry. So somehow there's a unifying approach to provide these maps. And the second question that I would like to state is the following, which is, let's say, infinitesimal question, or version of the first question, which is you take a vector fields of S1, okay, and then you try to find a good class of extension of this vector fields to the unit disk. Okay, and as we see in this talk, that the main result is on the infinitesimal earthquake and a class of vector fields, which we call them minimal Lagrangian. So the goal of this talk is not to convince you that these, let's say, vector fields are important, but the way we prove it, okay, the approach that we prove it, I think that it is nice. Okay, so let's talk about earthquake and infinitesimal earthquakes. I need to introduce some background on hyperbolic geometry. So the hyperbolic space H2 is the following space. This is the complex number of positive imaginary part, which is conformal to the unit disk. The boundary of H2, this is R union infinity, and this is S1, okay? So so in the last question, we will be interested on this model of the disk end of S1, okay? This is H2 and the boundary of H2. And what we will call geodesic, as you see in the picture, this is the blue things here. So it's either vertical lines or semicircle orthogonal to these vertical lines. This will be geodesic in H2. And now once we have this, I need to define to you a way to move inside this space. And to do this, let me introduce the space of 2 by 2 matrices. And I take the projective space of that vectorial space, okay, namely the set of all lines inside the inside the space of matrices. And then I define this the following set, which is PSL to R. This is the set for which the determinant is positive. The set of projective matrices for which has positive determinant. Okay, so what is the relation between this and the hyperbolic space? Because each element, each projective class of matrix inside PSL to R induce a transformation of H2, which is called isometry, which is the following. So this is a, how do we call this? Mobius transformation. So for each Z, you have AZ plus B over CZ plus D. And it is called isometry because it preserves some distance, okay? Okay, so now let me introduce earthquake map. Before that, I would like to give a vague idea of what are these maps. Okay, let's try. Sorry. Okay. Okay. It will be quick. So I will not be very clear here because I will give a formal definition later, but let me just give a rough idea of what are this object. So the thing is that this is related to the Teichmüller theory, namely the study of hyperbolic metric on surface. So if you take M be a hyperbolic metric on a closed surface sigma, let's say the surface of genus 2. Okay, so we have this hyperbolic metric. And now you ask the question, can we, how can you change this hyperbolic metric? How can you produce a new hyperbolic metric? One way to do this is the following. So you take a closed curve here, let's say this smaller curve in red. And that what you can do is that you cut your surface along this red curve, okay? So what you will have two parts like this, okay? And then you glue back these two parts, this sigma, let's say let's call this sigma 1, and this is sigma 2. And then you glue back these two parts by a twist, okay? So namely, you identify this red curve, but not by identity, but by doing some twist. So the result in, sorry. So what you will get in the end is of course the same topological surface with this closed curve L. And then in fact, what the metric will change outside the neighborhood of this L. Okay, so outside L, the metric is the same. And now if you cross this neighborhood, the hyperbolic metric change. And this is a particular case of earthquake along a geodesic. Another question that you may ask is that, can we obtain all the hyperbolic metric like this? And the answer is nearly yes, because it is yes if you allow to do such surgery along a complicated object, more general than closed geodesic, and these objects are called geodesic lamination. Okay, so if you allow to do if you allow to do earthquake along a geodesic lamination, then you can get any hyperbolic metric just from a particular ones. Okay, so this is the rough idea of earthquake, but for okay. Okay.
Sorry, Farid. Can I ask a question?
Yes.
you say that you can obtain every hyperbolic metric.
Yes,
That means like every hyperbolic metric on the on this Riemann surface.
yes, exactly.
Okay, just by doing earthquakes.
Yeah,
Okay, okay. Thank you.
yes. So for today, I will not talk about this point of view of Teichmüller theory and hyperbolic surface. So I will give a definition which works in the universal cover. But in fact, if you think a little bit about it, it's generalized this construction. Okay, so what is geodesic lamination? I told you that there is some object which allow us to do, which has more flexibility. And this object is called geodesic lamination. So geodesic lamination on H2, this is a closed subset of H2, which consists of a collection of disjoint geodesic. Okay, so what is this complicated thing? Just keep on mind, for those who don't know this kind of stuff, just keep on mind the union of finite geodesic on H2. Okay, like this picture. This is a particular case of geodesic lamination, but it could be very, very complicated. Okay, I need another terminology, which is a strata. What is a strata of lambda? So this is either a leaf of lambda, a leaf, it means one geodesic of lambda, or a connected component of the complementary of the lamination. Okay. Now, what is an earthquake? So a left earthquake along a geodesic lamination lambda. So first, this is a bijective map from the hyperbolic plane to itself. Okay. Such that this is the property that I want you to keep on mind. Okay. Because the second one is quite technical. So for any stratum S of lambda, so remember that stratum is either a geodesic or a connected component of the complementary of elimination. So there is an isometry A which depends on S, okay, such that the restriction of E to S is AS. So these earthquake map are somehow piecewise isometric map. Okay. And now there is here a word left, so I should give definition, but don't worry if you don't understand very well this second part. So for any two strata, S and S prime, the comparison map, which is by definition between two plaque, S and S prime, which is by definition the following, AS minus 1 composed with AS prime, is a hyperbolic isometry which translates to the left as seen from S to S prime. So I will not explain this part. Just focus on this first part. So for example, if you don't have geodesic lamination, if it is empty, we can make the convention that isometry is a particular case of earthquake. Okay. So let me give example. Example is the following. You take Z, you take Z if real part is negative, and you take exponential TZ if the real part is positive. And this is the picture in fact. Okay. So this is a left earthquake. So if T positive, let's say this is left earthquake. If T negative, this is right earthquake. So this is how the map behave on hyperbolic plane. Okay, so what is the theorem of Thurston? He states that any orientation preserving homeomorphism of S1 is the extension of a unique left earthquake of the hyperbolic plane. So, this is this answer to the first question. I mean, this provide a class of maps which extends any orientation preserving homeomorphism. He called it in his paper geology is transitive. So geology, I guess I think you guess why we call this geology. And transitive, this is related to the explanation that I made, which is that if you can get any hyperbolic metric just starting from any point, you can reach any hyperbolic metric. Okay, and this is the answer to the question of Alex. Okay, when you have such things, we call the action is transitive. When you can reach any things just by one point, you say that your action is transitive. Okay, and then after a few years, Mess gives an anti-de Sitter proof of Thurston earthquake theorem. So the main motivation of Mess is not to provide to understand earthquake, but to study the deformation space of particular Lorentz manifold. And when he studied this, he discovered this proof.
Farid, I have a question.
Yes.
Observation. So, earthquake are discontinuous, yeah?
Yes, they are
Like,
continuous, as you see in the
yeah, okay. But their extension to the circle, you assume them, or maybe they are always, this is the question, homeomorphism, yeah?
Yes, they are always homeomorphism. This is the
So,
quadratic theorem of the Thurston theorem.
okay, so what is the point? I mean, why we are not asking, why we are not starting with any transformation of the circle, not necessarily continuous, and we ask if it can be extended by something. We are restricting ourselves or to only homeomorphisms of the circle.
Because this is a necessary condition. If you start from earthquake just by this definition, then you can prove that it extends to S1 to orientation preserving homeomorphism.
Okay.
So you cannot relax this condition. Yes. Okay. So if there are no more questions, I move to talk about infinitesimal earthquake. So here we will play the same game in the sense that these are vector fields which are piecewise Killing vector field. So let me explain first what is Killing vector field. So Killing vector field on H2 is a vector field whose flow preserves the hyperbolic metric. Namely, it is a family of isometry of H2. Okay. So this is a basic example. Okay, you take exponential tz. This is isometry in H2. You take the derivative. This is a Killing vector field. Okay. And then what is definition of infinitesimal earthquake is the same as earthquake, just you change the word isometry by Killing vector fields. So a left infinitesimal earthquake along a geodesic lamination. So this is a vector field on H2 for which along any stratum of S, namely a leaf or a connected component of the complementary of the geodesic, there is a Killing vector field, Ks, which depends on S, such that the restriction of E is Ks. Okay, and there is also the second technical definition requirement. And again here, I mean, maybe here it seems somehow. I mean, the thing is that if you have a hyperbolic surface, this object can appear in different ways. Okay, so for those who know the Teichmüller theory, you know that there are some functions which are called the length. Okay, you take a geodesic and you measure the length. So this gives you a map from the Teichmüller space to R. So the differential of this map is one form of the Teichmüller space. And for those who know, the Teichmüller space has a symplectic structure. And in fact, the symplectic gradient of the length is exactly an infinitesimal earthquake. Okay. Again, this is maybe not clear from this definition, but just to tell you that this maps appears in different ways. Okay, in the Teichmüller theory. Okay, again, example. I'm just take this the previous example. Okay, and I take the derivative. And take the derivative with respect to t. So this is an earthquake. I take the derivative left infinitesimal earthquake. However, in the definition, this is not always true that an infinitesimal earthquake is the derivative of one parameter family of earthquake. Okay, this is the thing. And what is our main result is the following. So this is analog of Thurston earthquake theorem for vector fields. So any continuous vector field on S1 is the extension of a unique left infinitesimal earthquake. Okay. So let me say that people know this for a particular case. So Gardiner proved this theorem for Zygmund vector fields. Okay, and in fact, this condition I will give. So our proof is different, of course, from Gardiner proof, and after that, I will give a characterization of Zygmund vector fields by using our approach. And typically, this Zygmund condition is the right condition to put in order to say that left infinitesimal earthquake are exactly the derivative of one parameter family of earthquake. If you are Zygmund, then this is correct. If not, you cannot say anything. Okay. So let me now talk about the anti-de Sitter geometry. So I take Q, which is minus determinant. So determinant is a multilinear form. But if you restrict to the space of 2 by 2 matrices, this is a quadratic form of signature 2, 2. The tangent space of PSL to R is identified with the orthogonal of M. So here the orthogonal with respect to this quadratic form. And so the restriction of Q to each of this vector hyperplane has signature 2, 1. And this is, when we have such things, this is a Lorentz bilinear form. And so what is the anti-de Sitter space? This is just PSL to R with this metric Q. So this means that for on each tangent space, you have a quadratic form of signature 2, 1. And for the expert, this is up to scalar, the Killing form. So this is a Lorentzian manifold of constant sectional curvature -1. So this is analog, let's say, of hyperbolic geometry in the Lorentzian world. The isometry group of ADS3, the identity component, let's say, is PSL to R cross PSL to R. So how such element acts on ADS3? So you take AB. So each AB induces a transformation on anti-de Sitter space, okay, which is just conjugation, okay, by A and by B -1. Okay, and now one may ask the question, what is the relation between, I mean, I give you a map from S1 to S1. What is the relation with this geometry? So to do that, we need to talk about the boundary of the anti-de Sitter space. So remember, PSL to R, this is the negative line with respect to the quadratic form Q. So Q is minus determinant, right? And then the boundary of anti-de Sitter space is just the topological boundary inside the projective space, which is the following. So this is the space of null lines, okay? So this is a projective class of M such that Q of M is equal 0, okay? But what is this space? So you have a matrix of determinant 0, which is non-zero. So this is rank 1 projective matrices, okay? Because in projective space, you remove, I mean, 0 does not give you a line. So M is non-zero. And so what is this space? The observation that one can make is the following. So for each M like this, you associate to determine a rank 1 projective matrix, okay? It's enough to know the image and the kernel. So the image and the kernel are two non-trivial lines, okay? So they define an element of the set of lines in R2, which is RP1. And so in the end, the boundary of the anti-de Sitter space is identified with S1 cross S1. Hence, if you have a map, the graph of this map will be something that lives in the boundary of anti-de Sitter space. So maybe one can tell the PSL to R is just a solid torus, in fact, topologically, and the boundary of the solid torus is S1 is a torus, so it's S1 cross S1. But I mean, this identification is nice in the sense that it is invariant by the isometry. It is equivariant, sorry, by the isometry group. So if you have a couple AB, which gives you an isometry of anti-de Sitter space, of course, if you apply it to M by conjugacy, as we learn in linear algebra, when you conjugate a matrix, does not change the rank. And so this action can be read here by just, so if here is AB, you act by the couple AB. So here will be just A of the image of M and B of the kernel of M. So this is the product action. Okay. Okay. The second ingredient that I need in order to explain the idea of mess is the notion of duality in the anti-de Sitter space. So definition, what is a space-like plane? So a space-like plane is a plane such that the restriction of Q to P is a Riemannian metric. Namely, so Q has signature 2, 1. If you restrict this Q on the tangent plane of P, you get signature 2, 0. So this is definite positive. So this is the picture. So this hyperboloid is the, let's say, the cartoon of the anti-de Sitter space in affine chart. And the space-like plane looks something like this gray region. And there is a fact, which is that any space-like plane is a copy of H2. Okay, so this disk is really the hyperbolic disk. Okay. And so, and in fact, we have an identification, which is that the set of all space-like planes in anti-de Sitter space is identified with the anti-de Sitter space itself. Okay, we say that the dual of the anti-de Sitter space is the anti-de Sitter space itself. So how this correspondence works, you take M, and then you take the orthogonal of M, okay, which is a 3, which has dimension 3. You projectivize, which is dimension 2. You intersect with anti-de Sitter space, and you get the space-like plane. Okay, so all space-like plane are obtained by this way. This is the orthogonal of some element in anti-de Sitter space. Okay. Okay, so now let me explain the mass proof of Thurston-Earthquake theorem. First, I need to recall what is Thurston-Earthquake theorem. So any orientation preserving homeomorphism of S1 is the extension of a unique left earthquake. So first, as we said, you take phi homeomorphism, then the graph is something which lives in the boundary of anti-de Sitter space, right? So here, in fact, I'm not giving, of course, I will just give a sketch. There are a lot of work to do. So here I'm drawing a picture, which is that the graph of phi is in the boundary of this hyperboloid. And here, in fact, there is a fact that you need to prove is that the graph of homeomorphism is contained in a affine chart in order to do such construction. And this is not true for any map from S1 to S1. So here you really need that your map from S1 to S1 is a homeomorphism to do this. Okay. So anyway, let's say that you take this graph inside this hyperboloid, and that's what you can do. Do you see? Okay. Yes, you take the convex hull of the graph of phi. Convex hull means the smallest convex set which contains the graph of phi. So it will be something like this. And then what you can do, so the boundary of this convex hull has two connected components. Okay. Let's take the connected components, which is the red one. Right? And so I fix now my favorite, I fix a copy of H2 inside this hyperboloid. As you see this horizontal H2 in the picture. And that's what you can do. You take X a point in H2, and you take Y the projection of X to the lower boundary. I mean the red part. Okay. I will come back to this word projection later. And then how do you define this earthquake? So the earthquake will be just m of x, okay? To each x you associate m of x. What is m? M is in fact the support plane of this red surface at the point y. So you have x, you project it to your surface, and you take a support plane, namely a plane which touch your surface in the boundary, but not in the interior. But this plane is space-like. And now if you remember, any space-like plane is the orthogonal of some element in the entity de Sitter space. So it can be written as the Pm, P script m, namely the orthogonal of m. And so you take what is your earthquake is just the evaluation of your isometry m at the point x. And of course, you need to prove that this is indeed an earthquake, which extends to your homeomorphism phi. So here there is, you should be careful about this word projection because I did not define it. In the picture, I just put vertical lines, but of course this is stupid things because vertical lines in the Euclidean eyes, I mean, this is not preserved by the isometry group of entity de Sitter space. I mean, there is a well-defined projection here. Once you understand this projection, this is roughly the idea of the proof of Thurston earthquake theorem. Yes, I think that how much? Yes, I think I will stop here for the first part. Thank you.
Okay, thank you, Farid, for this interesting first part. So, are there any questions about the first part?
Yes, I have some questions. You said that as soon as you have a homeomorphism of the circle, it suffices so that the graph is included in an affine chart.
Yes.
It seems strange. If you take, for instance, an isometry, don't you obtain a photon that is not included in an affine chart?
Yes, but the boundary of a photon is not isometry. So the boundary of a space-like plane is an isometry, is the graph of isometry. The boundary of a time-like plane is a graph of reversion isometry.
Okay.
And
yes, okay.
yes. Yes, and the boundary of a photon is related to, I think, I'm not sure, it's a leaf of this RP1 cross RP1. So, okay, attends. Yes. Yes, the boundary, I think that this is the image of M cross RP1 union RP1 cross the kernel of M. I think it should be something like this. The boundary of light-like plane.
Okay. Okay, thank you.
Yeah, okay.
And maybe I have another question.
Mhm.
This projection you use, it's the warped projection or it's a normal projection from H2?
I don't know what is the warped projection.
Okay, so the warped projection, it's when you write ADS3 as a product
Mhm.
of H2 cross S1.
Yes.
It's not an isometric product of H2 cross S1.
Yes, okay, yes.
I mean, follow this S1. This is what I call the warped projection. And that's not you do, no, right? You follow a geodesic orthogonal to H2.
I don't know, honestly. I don't want to say something stupid.
Okay.
So this projection, I mean, in the boundary, it has a nice interpretation. So this hyperboloid is foliated by two lines, okay? So in the boundary, if you want to identify this H2 to this PM, this is just you follow one, I mean, the foliation. So if you have a point here in H2 in the boundary, okay, you draw two lines, okay. So because it's a foliation, there is There is two lines which passes to these 2 points, and then there is two projection. In fact, there is a left projection and the right projection. So boundary, it has a nice interpretation, and after that, it's turned out that this projection extends to the interior using the product structure of your isometry group. Okay.
Okay.
Yes.
Nice. So you follow some kind of a light direction? Not really. You like you.
Yes, like in the conformal boundary. Yes, LP1 cross.
Okay. Thank you.
Welcome.
Yeah, I have a question. Can you please, Farid, explain how you go from H2 to H2 and not to a DS3? Because M is a priori is just in anti-de Sitter, no?
Yes, which is isometry. So it's an element of PSL2R, no? And so you apply it to X.
Oh, yeah.
So this is a Mobius transformation.
Okay.
And in fact, if the picture you see this Y is in some in some flat piece, you see from the picture that if you move X, there is a flat piece where this L does not change. And this is definition of earthquake indeed, because on the strata of lamination, of geodesic lamination, your earthquake is coincide with isometry.
No, excuse me. So you said that you have X, you project X on the boundary of the convex hull and you get Y, and you have support plane,
Yes.
which is space-like, and so it is dual to some point.
Yes.
Some point in ADS, and you see this as element of PSL2, and you
Yes.
apply it to X, yeah?
Exactly.
Yeah, okay.